as for today, another exciting section. And the big note about this stuff, so we're getting into some of the background and stuff so we can make sure that we have all the knowledge in order to be able to solve more problems when we get into applications. But just be prepared. This is chapter 6 is the hard stuff. So 6 part 1, 6 part 2. This gets much more difficult, but then we end the course, the last 3 sections are, most people just do much, much better. All right. So brace. All right. And then basically we need to make it till like the week after spring break, and then the remaining should not be as bad. Okay. Along those lines. So we talked about our functions, all right? And we haven't actually looked at inverse. So just to recall what an inverse function is, right? It is the opposite mathematical operation. What is the opposite mathematical operation of root x?
Squared.
Yeah, all right. So if this is f of x, then the inverse function is x squared, right? Technically with a restricted domain. And then just to refresh, because it's always good to know, what's the opposite function of e to the x? What is the inverse function? How would I solve that for the x? How do I bring an exponent down? What mathematical operation is that? Anyone remember? Logs. All right. Just refreshing. Oh, that algebra, right? All that algebra. And then just as a note, all right, inverse functions, they are symmetric. Over the line. Y equals, does anyone know? Huh?
Y equals 0.
Oh, that's a good guess. That y equals 0 is a pretty good guess, right? It's kind of our standard. It's actually the line y equals x. A function and its inverse are symmetric, all right, along the line y equals x. But yes, that was a wonderful guess. See, okay, good. I'm glad that we're starting to understand our guesses. So along those lines, a function and its inverse. So if I have the sine function and then the inverse sine function. So I want to plot this out. And typically we plot one full period, right? But I only want to, because the inverse function is restricted. Because also, in order to be a function, do we remember what that test is called? For a function to be a function?
Vertical line.
The vertical line test. All right. So a periodic function, if that's symmetric, then that would be periodic like this. That fails the vertical line test. All right. So an inverse function for a trig function usually has a restricted domain. So I'm just going to graph a restricted domain of the sine function. Okay, so this is, let's call it f of x. F of x equals sine of x negative 1 to 1, right? And remember, sine is odd, so it's negative flipped, all right, across the origin. But the inverse function will then look really, really similar. With all the same corresponding values. And graph not to scale. So all of these are then symmetric. About the line y equals x, and we have our function, right, and its inverse. So the graphs look very similar. The point is, all right, is that just like with square root, e log, add, subtract, multiply, divide, in order to get rid of sine, guess what we're gonna do? The inverse sine. Inverse sine. All right, so just like we don't have all this nice fancy notation, okay, for trigonometric functions, so we just say function and its inverse.
Could you go back up just for a second so I can finish right that last, yeah, last. Okay, got it.
All right, then. Good. So along this then comes to the calculator. So sine inverse of a number is still some number. All right, guess how we do this? All right, if possible, we're going to do the exact value. Does anything on your unit circle have 1/3? There's only 3 big numbers to remember, right? 1/2, √2/2, and what's the other one? √3/2. √3/2. Is 1/3 any of those? Nope, which means calculator. All right, on your calculator, the inverse function is the second button above the sign. So let's see, what mode are we in? I'm in radians. Sine inverse of 1 divided by 3 gives me 0.34 rads. And that's the point. So the inverse function can work backwards, all right, to get us the angle. A function and its inverse. And this is going to become massively important when we start solving, because I don't want to know what the sine of the angle is. I want to know what the angle is, right? At what angle do I need to measure to find that height? So that's why we use inverse functions. Now, we can be more precise when we have something that actually is on the unit circle. So 1/2, we just said, is on the unit circle. And specifically, we can have -1/2. And so what angle does that correspond to? What 1/2 is pi over, what is it? Not 4. 6, pi over 6, right? What sine of what angle? I could also write this as theta. Theta equals that. And then take the sine of both sides. This is how we solve. Take the sine of both sides. That becomes sine of sine inverse of -1/2 equals sine of theta. And then the whole concept, a function and its inverse, just results in the value. So this becomes -1/2 equals sine of theta. This is to find the exact value. And then we look up and I'm like, okay, for what value, and we already said, is pi over 6? And now here's the part that actually revolves around the graph. Okay. It goes up to 1 here and back to -1 here, which means that the only options are -pi/2 to +pi/2. All right, that is the restriction. So -1/2 could be lots of values for the initial function, but when you're actually solving it, it's always going to be a reference angle. So it's always basically those angles in quadrant 1, it's either positive or negative. All right, so even though whatever 11 pi over 6 is the actual angle on the unit circle, that actually results in just negative pi over 6. And actually some even and odd properties are going to help us with this as well, because that negative is the hard part to identify. Was that positive, all right, pi over 6, or negative pi over 6? Because I have -1/2 here, and that's what implies it's negative pi over 6. All right, so the whole point, a function and its inverse, or inverse and its function, all right, always result, all right, in the opposite function, which means sine inverse of sine of pi over 8 is just what number? Pi over 8, right? Square root of 7 is just 7. All right. It is a function and its opposite. We just don't have nice notation, right? Add 7, whatever, x plus 7 minus 7 is just x. All right. So this is the function and its opposite, its inverse. And so again, this is really an algebra concept. We're just kind of generalizing it, all right, to trig. The difficult part is this restriction. Now, the good news, most of the time, it's not going to matter. I'm going to show an exception case after we graph cosine. All right, so again, I'm only going to do half a period because the inverse has a restricted domain. So, as best as I could. Same thing, all right? Cosine is also restricted. Oh, and that value will be pi. Pi 2. Cosine inverse is also a restricted function. Again, in order to actually be a function, because at these endpoints, right, that's where the graph turns periodic. So the inverse function always has a restricted domain. All right, it's only half of a first period. good. But the big part is that once again, right, in order to use this and to find an exact value, I could set that equal to theta, then take the cosine of both sides. So I have cosine of cosine inverse. Cosine of cosine inverse goes away. Gives me cosine theta equals negative root 2 over 2. And then what reference angle corresponds to root 2 over 2 for cosine? Or sine, actually. Pi over 4. Now, it seems like I would say, okay, so how about negative pi over 4 corresponds to theta? This is the annoying part of the restriction. All right? Negative pi over 4 is over here. All right? This one is limited between 0 and pi. So what's the next value for negative root 2 over 2? Root 2 over 2 has to be a multiple of pi over 4.
Oh, I see.
Right? So it's not pi over 4. It's not negative pi over 4. What's right here? Negative root 2 over 2 is something around here. So what's in between pi over 2 and pi? It is a multiple of pi over 4.
3 pi over 4.
3 pi over 4. And that's the annoying, those are the annoying ones. Now, the good news is, as long as the domain is restricted, 0 to pi, all right? So all the values for cosine inverse are positive, all right? The values for sine inverse are actually easier because it's negative or positive, so you just mess with that. But as long as that value is positive, cosine inverse of cosine, it's just going to be pi over 12. So that is its opposite function. So the exception comes to something like this. Cosine negative 1 cosine of negative 5 pi over 3. So we do this a piece at a time. Always start with the initial function. So cosine of negative 5 pi over 3. All right, so I ignore the inverse and I'm just looking this guy. Okay, so to my unit circle I go. Negative 5 pi over 3 angle, and actually I can even make this easier. Is cosine even or odd?
Even.
Even, which means what happens to that negative? Take it out, bye-bye. So this actually becomes cosine inverse cosine of 5 pi over 3. Even. Okay, so 5 pi over 3, that one's a little bit easier. 5 pi over 3, so that's 6 pi over 3, so that's somewhere about there. Which again means my reference angle is pi over 3. Cosine of pi over 3. One half. And then is cosine positive or negative in this quadrant? I didn't hear what you said. Positive. Positive. Oh, good. So that means cosine of negative 1/2. Sorry, positive 1/2. Cosine of 1/2. And then basically I do the same thing. I look and I say, okay, all right, given the restriction, all right, where it is about half, all right, cosine once again is half, we just said it. That results in then pi over 3. So notice that that one, you kind of need to do it a piece at a time. So cosine inverse of cosine, it's not just negative 5 pi over 3 and I'm done, all right? Because the inverse function, it only exists from 0 to pi, I know it can't be negative. Now, the other thing is you can just quick find the reference angle and be like, oh, I bet that's it. All right, so notice how simple that one is. Cosine inverse of cosine, done. Cosine inverse of cosine of a mess. All right, and that's because of the restriction on the domain. Take it a piece at a time and then use the graph. Now, here's the good news. Your calculator, you can graph it. All right, so you'll always remember, if you can't remember, oh gosh, what's the domain? I can't remember if it's 0 to pi or if it's negative pi over 2 to pi over 2. All right, those are the trickiest ones. Most of the time, cosine, cosine inverse, they cancel each other out. But you got to mess with what that angle is on the inside. All right, similarly, let's do the tangent inverse graph. And the good news, tangent is probably the easiest one. Because the tangent graph is one of the easiest graphs that exist for trig functions. Orange. Okay, we got a lot going on there, just because there are both vertical and horizontal asymptotes. But here's the best part. How does the inverse tangent function look in compared to the tangent function? Besides my bad drawing. Is this the entire, for the blue line, is this the entire tangent graph? I mean, one period of it. Did we even get a full period of sine or cosine? No, this is the entire first period of the tangent graph, which means that there is no restrictions, all right, for the tangent inverse function. And that's a big deal. Okay, yes, it doesn't have all the periods of tangent, but that is one entire period. And basically, the tangent graph looks like what polynomial? Cube. What does this one look like? It's one of the other 6 basic functions. Cube root. So basically we have the cube and cube root. And that looks exactly how it's supposed to look. So now that means the tangent function of its inverse, there are no crazy exceptions, and beware, cosine is the worst one with that. Cosine and its inverse, because cosine was an even function, so it wasn't even symmetric about the axis, and that's when all the problems come into place. But sine and tangent were both initially odd functions, and so are their inverses. Which means that, oh, we can use those even and odd properties. For the cosine graph, all right, we know that cosine was even. Is the inverse cosine function still even? What does even mean again? Symmetric about the y. Is this symmetric about the y? No. Is this an odd function? Is this symmetric about the origin? So this is neither, which most graphs are, all right? But that becomes why it becomes a problem. It was an even graph and the inverse is neither. Sine, tangent, cotangent, and cosecant. They were all initially odd. All their inverses are odd. Cosine and secant were even. Their inverses are neither. And that's why it's annoying. So see how those properties just keep helping us? All right, so what this means is that then I can evaluate with a bunch of inverse functions. And every time it's all about letting the inside, dealing with the inside, making a triangle if needed or using the unit circle, it doesn't matter, it works both ways. And then putting that back in and finding whatever you're evaluating. So notice I no longer have sine of sine inverse, all right? I'm rotating what the function is at the inverse. So I'm going to start with the inside. Let theta equal tan inverse of 1/2. Take the tan of both sides. And tan of tan inverse, right, goes away. And 1/2 might be 1 on the unit circle, but it's not springing anything to me. But I don't know tan as well, unless it's 1. So that means let's create the triangle, and be aware we can always do this, right? So you don't have to use a unit circle basically ever. You can always just create the triangle. Tan is what over what?
Opposite over adjacent.
Opposite over adjacent, right? So we're getting SOHCAHTOA, we just keep saying it to ourselves. Opposite over adjacent, calling that one theta. And so then 1 squared plus 2 squared, square root. Okay, so root 5, so definitely not 1 on the unit circle. And now back to our problem. So since I let theta equal that whole inside, now I have sine of what? Given my substitution. It's not sine of tan inverse of 1/2 anymore, it's sine of let theta equal tan inverse of 1/2. Sine, this becomes sine of theta. Right? We had a substitution to create. So then all I have to do, what is sine of theta? There's my triangle. 2 over root 5. Do we see how, like, I know that, and that's the whole point. Oh my God, this looks so complicated. I don't know how to deal with this. Like everything in trig, we make the triangle and it simplifies so cleanly, right? We talked about KISS, right? Keep it simple, stupid. It's not supposed to be hard, okay? Now, we could do KIS, keep it simple. I like the additional S Because it's supposed, like, if you're struggling, you're doing it wrong. It's supposed to be easy. Okay, and along those lines, we have a bunch of restrictions on all the following inverse of all the reciprocal functions and their inverses, which is always a mess. Now, the big thing here is that most calculators, right, they don't even have a key, right? I see sine inverse, cosine inverse, tan inverse. Okay, but similar to doing reciprocal functions of the initial trig function, all right, the trig function, the reciprocal, instead, in order to do a reciprocal function, so secant for cosine, all right, instead you transfer the reciprocal inside, all right, the equation. So secant of of 3 becomes its reciprocal, cosine inverse, and I flip, all right, the reciprocal of what I'm doing the inverse of. So it's both pieces. And then the point of that, then calculator away. We could make the triangles and such for those, and we will on better problems. And these are all rads. Sine inverse of -1/4. And that actually comes out as 1/4. I was like, didn't think it was that perfect. It's actually 2.5, 2.6, da, 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 da. I was like, -1/4. Seemed unlikely. So for those ones, most of the time, if we need, we will draw the triangle and find the exact value. But just so you know how the calculator works, all right, take the function, flip it to its reciprocal and the expression on the inside. When we're trying to find the exact value, so those ones we weren't trying to find the exact value. This is all about using the function and its opposite. Just like all solving, all right, you do PEMDAS in reverse, okay? So always do the easy stuff first. And the best thing is to think of a trig function like a square root, right? Do you immediately square both sides? You do that first with every problem all the time? No, it's pretty much the last step you do. So you want to isolate that radical, right? Same thing, you want to isolate the trigonometric function. So what should I do first for this problem?
Move 3.
Do what? Move the 3, yes, okay, I thought I said multiply.
No.
Yes, move the 3, AKA divide the 3. So divide both sides by 3. Now I have my trigonometric function isolated. And that's basically what we do every time. Then I'm going to take the cosine of both sides. And then we need to identify what is cosine of 2 pi over 3. Some about 1/2, and then basically identifying if it's positive or negative. Negative. And then we're all done. Divide by 2. All right, step by step. Oops. Three tan inverse x equals 1. All right, so same thing. Divide by 3 first. Isolate that trigonometric function. And then once again, I ask, how do I get rid of an inverse tan?
Both sides by the tangent.
And then how, see, it works the same way in reverse. How do you get rid of a tan? Not for this problem, just in general. How would I get rid of a tangent? Inverse, right? Function and its inverse. I know it's a new operation, but as far as algebraically, it's really, really old, right? We're so used to add, subtract. Oh, if it's x plus 7, I subtract 7 from both sides, all right? It's just the same function, slightly different. And you see all this when you first do logs, and that's the first one that's kind of weird. In order to undo an exponent, you take the log of both sides. In order to get rid of a log, you raise both sides by that exponent, right? So that's the first one that's kind of funky. And then I'm down to something that I should know. Tan of pi over 3, which is actually sine of pi over 3 over cosine of pi over 3. I don't have tan memorized. Sine of pi over 3 is root 3 over 2. Cosine pi over 3 is 1/2. Okay, so leave a change. Okay, it's root 3. Okay, you could just look on your unit circle, right? Again, I only have 3. I only have 3 angles memorized. Sine and cosine for pi over 6, pi over 3, and pi over 4. And really, because pi over 6 and pi over 3 are just flipped for sine and cosine. So again, the whole point is, I know that unit circle is helpful, but all that pairs down to basically like 2 angles. Okay. And okay, so now cosine, sine inverse. Cosine, sine inverse, negative 2. So always start with the deep inside. When you have a function of a function, and I can draw the picture on these too. Just happens that root 3 over 2, one happens to be one that I know. Skip up. So actually, let's back up a step. We said, all right, sine, cosecant, tan, cotangent are all odd. Similarly, all their inverses are odd. Sine inverse, cosecant inverse, tan inverse, cotan inverse are all odd. That's really good news for us. Cosine and secant are even. The most annoying case, cosine inverse, secant inverse are neither. So we have to deal with whatever sign is there. Sign, S-I-G-N. All right. Well, when I have even and odd functions, it means I never have to deal with negatives. All right. And that's super, super good news because negatives they just mess everything up. So because sine inverse is an odd function, this actually becomes negative sine inverse of root 3 over 2. And this is because odd. Similarly, all right, now I have cosine of a negative. And cosine is even, so what happens to the negative? Go ahead. Yeah, it just drops, right? That's actually the best part. We just drop it, it's done. All right, and this is because it's even. All right, so cosine is even, right? And sine inverse was odd. That's how we're able to manipulate those negatives. So notice I had a negative, right? It then came out front and then just basically went away. If you deal with those even and odd properties, and I can't emphasize enough, knowing stuff is even and odd is so helpful because all those positives and negatives really like interfere. Okay, so now back to let theta equal sine inverse of root 3 over 2. And now I don't have a negative. And I'm going to take the sine of both sides. And then we just ask, theta, for what angle is sine of theta equal to root 3 over 2? Here, I'll do the hard part, pi over 3. Is everyone okay using their unit circle? We're all right? Okay, now back to my function. So I had cosine of a bunch of stuff. Cosine of sine inverse of root 3 over 2, which became cosine slope of theta, which is actually cosine of pi over 3. And then I'm just finding cosine of pi over 3. Which is 1/2. And I mean, again, notice that a lot of this, I mean, that's unit circle. I mean, in order to jump this step to this step, I mean, it's just unit circle. Right here, unit circle. So once again, all right, let's deal with that negative. Sine inverse is odd. So that pulls it out to the front. And then secant is even. Which drops it away. So that negative all the way deep inside. And I mean, if it's an odd function on the outside, then it just pulls all the way out to the front. And you just deal with that at the end, right? Just attach it on whatever your solution is. Even and odd properties make those way easier though. Once again, then let's take the inside. Let theta equal sine inverse of 1/2. Now everything's positive and beautiful. Take the sine of both sides. And then sine theta equals 1/2. For what angle does that occur? Nope. Had a 50-50 shot, really.
5/6.
5/6. And then back to our equation. Secant of that whole thing. We'll get rid of that. And since we have secant, but I don't know what secant is, anything. Cosine of pi/6. You have 1 all over √3/2. Leave it, change it, flip it. 2 over √3. All right. Okay, so this comes into kind of the theory part. An identity that we have been using and others that we're familiar with, right? When one side of the equation equals the other side of the equation, right? I have a binomial squared, makes a perfect square trinomial. A big one we use all the time is the fundamental identity of trig. Those are identities. One side equals the other side of the equation. What we typically solve, right, what we're most used to solving is conditional equations, where you solve this and I get x equals a number. All right, and that's basically what we just did. But one of the other things is using these properties to identify, right, what's known as establishing identity, showing one side of the equation equals the other side of the equation. And for these, there are a couple of main techniques. And these aren't going to be anything that you're unfamiliar with. Convert to sines and cosines. And that's basically what I do all the time, right? I don't even know secant or cosecant or tangent even of anything because I convert everything to sine and cosine. All right, and these are in order of how you should approach the problem. 2, common denominator. Factor. We're going to discuss a little bit about factoring as well. All right. The next option is using identities and or definitions, and specifically when we talk about that, we mean our trig identities. All right, our trig definitions of reciprocal functions and some difference products, sum to product, product to sum. All right, so that's basically everything on the front of your cheat sheet. And the last, and this should always be the last, use the conjugate. All right, that might be a word that you've seen that seems familiar, but you're probably a little rusty on the definition. The one you're most familiar with is the complex conjugate. If I have an equation, a complex number, a plus bi, all right, the conjugate of that, and in this case, the complex conjugate, is the exact same thing, but the opposite sign. And again, sign, S-I-G-N. You multiply by the conjugate because when I have, x plus 3, x minus 3, I multiply those out. What happens to the middle term when you FOIL those?
Cancel each other out.
They cancel each other out because one's positive and one's negative. All right, it's also referred to as a difference of squares. Okay, you are creating a difference of squares. All right, and that's what a conjugate is. It doesn't have to be the complex conjugate. It could just be whatever you're looking at and flip the sign. Okay, let's look at some examples. So our goal is always to simplify, right? Establishing an identity is showing one side equals the other, but most of the time we just want to simplify to something that makes more sense. So going through that list of techniques, technique 1 is convert to sines and cosines, and this looks like the definition of that, right? Cotangent is sines over cosines. Cosecant involves sines and cosines. So cotangent is specifically cosine theta divided by sine theta, divided by cosecant is 1 over sine theta. And then algebra, right? We've talked about it a million times. What do we do here? Leave it, change it, flip it. And actually, while I'm at, convert to sines and cosines using reciprocal and quotient identities. Now, those happen to be pretty common ones, but just as an FYI. All right, then we're going to leave it, change it, flip it. Oh man, look at that beautifulness right there. And so something that looked initially more complicated, simplified to simply just cosine. So this one actually has an equality in it, which means basically you need to show the left side equals the right side. The best strategy for these is to take the more complicated side and adjust that one. Looking at the left side here, looking at the right side here, does either side look more complicated? No, they're actually almost identical, right? Okay, the cosine is crossed there. So it actually doesn't matter whether you take the left side or the right side. So I'm going to start with the left side, cosine over 1 plus sine. Now I need to, and this is what establishing an identity is. I need to adjust this to make that side equal the other side. And basically I go down my list, same as before. All right, sines and cosines, nope. Definitions, there are none. Factoring doesn't help. Common denominator, nope. The only thing, all right, that looks like I could do anything with is messing with the conjugate. And how I have that 1 plus sine there, that's kind of an indicator that, oh, maybe I can mess with that. Now, be aware, conjugate, it was listed as number 5 for a reason. That is your last step out of you're out of other options, because it always gets worse and it might not help, depending upon how complicated it is. But this one, there's literally nothing else to do. So I'm going to multiply by the conjugate. And everything we do, I'm not changing anything, right? 1 minus sine theta over 1 minus sine theta. That means I'm actually multiplying. What is this whole thing? 1, okay? We're not solving these, and that's the big trick. These aren't solves. These are simplifies, re-expressions. Now, FYI, you can FOIL, but this is like the definition of where the box starts to become more helpful. For those unfamiliar with how boxing works, all right, so I'm doing the denominator here. Take one expression, line it up across, and the box can extend to 5 by 5, 3 by 3s, whatever it is. Each term aligns with one box, right? Then take the other expression and each term aligns with one box. Then you multiply in to each piece of the box. So 1 times 1, sine times 1, negative sine times 1, and negative sine times positive sine. I also like the box. Now again, it's just an alternate version of FOIL. So if you prefer FOIL, go ahead. As a note, boxing becomes much more helpful in trig because FOIL really is nice when you just have two easy polynomials, but with lots of sines and cosines and secants, you just need to keep your pieces separate, and box is the best way to do that. And also in the box, I see a positive sign and a negative sign. Oh, look, so that goes away. All right, so what I end up with here, so in the numerator, I have cosine theta times 1 minus sine theta. I don't know if I want to multiply that yet. I'll leave that alone. And in the denominator, I have 1 minus sine squared theta. So when you come out of the box, when you write your terms out of it, you add your terms together. Multiply into the box, sum your terms out. Okay, so, all right, that's what I see right there. It doesn't quite look like the right side. Okay, I'm trying to get 1 minus sine theta divided by cosine theta. But down here, 1 minus sine squared theta, does that ring any bells? What does that kind of look like?
It's one of the identities.
That looks very similar to the fundamental identity of trig. Right, so note, sine squared theta plus cosine squared theta equals 1. That is the fundamental identity in trig. If I take this identity and I subtract sine squared from both sides, because that is an identity, I can move stuff around. So if I move that over, now look at that. This is actually still the fundamental identity. It's just slightly in a different expression. And this happens a lot. This concept using specifically the fundamental identity like this, all right? Because those other identities, remember tangent squared plus 1 equals secant squared? You could actually write that same thing as secant squared theta minus tangent squared theta equals 1. Right? So you can move that stuff around, all right? It's just whichever way you prefer to have the form. All right, so now substituting. And then, all right, I see a cosine on top, I see a couple of cosines on the bottom. That will cancel with one of those, because remember cosine squared theta means cosine theta times cosine theta. And then that leaves us with, I believe that was the other side. Now, notice what I'm doing each time, okay? With these establishing identities, with these simplifying equations, you want to identify what you're doing. Multiply by the conjugate, substitute sines and cosines, common denominator box. Make sure your work is clear, all right? Because otherwise it starts becoming magic math. Oh, like, and especially I see it a lot with identities because guess what the answer to this is? That. And you're like, oh, okay, let's make up some crap to make that look like that. No. Okay? The point is to get here to here with a logical process. All right, let's look at, we got time for one. Okay, so. All right, so this one again, I'm just simplifying. I don't know what the answer is. What do you think we should do? So what is technique 1?
I get sine and cosine.
Convert to sines and cosines. Okay, let's see. Done, 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 done. So really just cotangent. So I could do that and that might help. But what seems maybe more? So maybe that helps. And I don't know, sometimes I could try that. But it looks like I see, what is technique 2? Common denominator. Ah, that actually looks like I might be a little faster. And I can still come back to sines and cosines, but I want something that does the most in one step. So I think common denominator here is going to be the most helpful initially. Now, here's the other thing. I see people get way too lazy with common denominators. In order to create a common denominator, right, of 1/2 plus 1/3, what are you doing to each piece?
Multiplying it by the, well, like this side, you'll multiply it by cosine.
Hold on. Let's do this one.
Oh, that one?
Yeah.
You need to multiply it by 3. 3 over 3.
Ah, thank you. That's what I was looking for. Okay, it's 3 over 3, 2 over 2. Okay, don't get lazy with your common denominators because yeah, I see it. Oh, I'll multiply that one by 3 and that one by like. With so much going on, we need to remember. I mean, that's an arithmetic skill, right? But we've gotten so good at that type of thing over time that we're skipping these steps, and now it's more complicated, and it's going to come and kill you. So this one multiplied by cosine theta over cosine theta. Multiply this one by sine theta over sine theta. And then let's see, let's multiply this in cosine theta plus sine theta cosine theta all over sine theta cosine theta plus cotangent theta times sine theta minus sine theta cosine theta all over sine theta cosine theta. And then the whole point of common denominator, of creating a common denominator, is to put it over then that common denominator. And I'm gonna see if we can kind of kill two birds, one stone here. Now I want to see if, because actually now I'm multiplying by sine. I think I have some good news. So I'm going to convert that cotangent. Because I actually see now that is helpful. I have a cosine in the denominator times a sine in the numerator. And also notice plus sine theta cosine theta minus sine theta cosine theta. That and that cancel out. So now I have, let's see, cosine theta plus cosine theta all over sine theta cosine theta. And then I always see people mess this up. Cosine theta plus cosine theta, what is that? 2 cosine thetas, all right? Cosine theta times cosine theta. Cosine squared theta, right? I was like, I know that's an easy thing, but just be careful. So this becomes 2 cosine theta all over sine theta cosine theta. And then I'll get it. Cosine theta cosine theta. That becomes 2 over sine theta. And I could leave it like that, but I can do one more step just to get rid of the fraction entirely, which would be what? Something over sine theta is actually what trigonometric function? Cosecant. So, all right, all those reciprocal and quotient and all that stuff that we did initially, that's all coming back heavily. Okay, so the graphing we're going to use kind of sporadically on and off, even and odd we're going to use all the time. All right, but that left side of your cheat sheet, all right, that's going to be a big piece. All right, any questions? All right, got lots of good stuff to do this weekend. All right, you guys have a good day.